Welcome to lecture number 13 for ECE 321 Analog Electronics, two-port models. Now what we did in our last lecture is we looked at a transistor circuit where I would bias it in the active region. That was DC analysis. We're now going to look at AC analysis. What happens when you apply a sine wave into it? To do that, we're going to look at a generalized Thevenin called a two-port model. Now, Thevenin equivalents always cause confusion in circuits 1. People have done them, but they don't really understand them or like them. Thevenins can actually really simplify the analysis of amplifiers, so we're going to be using that. Two-port is a generalized Thevenin when I have the Thevenin at the input and Thevenin at the output. So, backing up, what is a Thevenin equivalent? A Thevenin equivalent is, if you look at a circuit like so, and I buried the load attached to it, what's going to happen is the voltage at the load versus the current at the load is going to follow a straight line for a linear circuit. When VL is infinity, I'll have some voltage. When VL is short, I'll have some current. That's the x-axis intercept, y-axis intercept. And being a linear circuit, 2 points determines a line. I'll have a line between the two. As I vary the load, I'll be somewhere on the load line. The idea behind a Thevenin is that in terms of the output characteristics, I don't really care how you generate that load line. Any circuit that has the same load line behaves the same as seen by the output. So I replace the circuit with the simplest circuit that I can that has the same load line. And that's either the Thevenin equivalent, a voltage and a resistance, or the Norton equivalent, which is a current source and a resistance. We'll be using the Thevenin in this class. That'll give you the two-port model. So, for example, suppose, let's go back to the circuit. For this circuit, to draw the circuit equivalent, if I open up the circuit right here, the open loop voltage will be 7/10, 7 volts. If I were to short it, I'll have 10 volts over 3K, 3.33 milliamps. That's the y-intercept. So any circuit that has this characteristic will behave like that. So if I take the Thevenin equivalent, this will be your 7 volts, the V Thevenin. The resistance, let's see, 7 volts over 3.33 milliamps. Gives you the resistance. And that would be my Thevenin equivalent. Another way to think of it, these two circuits are the same. So whatever I do to one, do to the other. To measure the Thevenin resistance, what I do is I turn off the input, make that 0 volts, measure the resistance. On this one, I turn off the input, measure the resistance, and I've got 3K to ground, 7K to ground. That's also 3K in parallel with 7K. So that would be the Thevenin equivalent. And you've got two parameters, kind of three ways to calculate it. I've got the open circuit voltage, that'd be V Thevenin. That's this guy right here. I've got the short circuit current. You short the output, how much current do I get? That'd be V Thevenin over R Thevenin. And I've got the slope. That would be the Thevenin resistance. If I turn off the voltage source, make this 0 volts, what resistance do I see looking in? That's your 3K in parallel with 7K, or 2.1K. So there's your slope. And that would be I, and V equals IR. R is 2.1K. That's actually 1 over the slope. A two-port model looks like this. At the input, well, kind of one way to think about it. If I take the output and tie it to 1 volt, this is the Thevenin equivalent at the input. If I take the input and tie it to 1 volt, This is the Thevenin equivalent at the output. This is an amplifier, so in general this isn't just a voltage, it's a voltage-controlled voltage source. If I double the input, I should double the output. It's an amplifier. So likewise, a sine wave in gives you sine wave out. Likewise, at the output, sine wave in gives you sine wave out. Two-port models work both ways. At the input I have a Thevenin equivalent. At the output I have a Thevenin equivalent. So really the two-port model is really just Thevenin equivalent. It's double the work because they need the Thevenin equivalent at the input and Thevenin equivalent at the output, but it's just a Thevenin equivalent. To find the two-port parameters, what I like doing is drawing the two-port model and seeing what test do I do to the two-port model to find each component. Do exactly the same test in the actual circuit. The two have to match because they're equivalent. So for example, suppose I want to measure AI. What I would do is I would apply 1 volt at the output, measure the voltage at the input, and that voltage is AI. To determine A out, what I would do is apply 1 volt at the input. And measure the voltage at the output. That'll give me A out. To measure Rn, this is where it gets a little bit trickier. A couple ways to do it. One way is I've got this AI getting in the way. I'm going to short the output. That makes V out equal to 0, and this goes away. Measure the resistance at the input. If the resistance isn't obvious, what I could do is apply a 1 volt test and see how much current I draw. Then from V equals IR, the resistance will be the voltage divided by the current. Likewise, to find the output resistance, what I'll do is I'll short the input. That sets A out equal to 0. Measure the resistance looking in here. Now it's important that you short the input to find R out, you short the output to find R in. That affects the measurement through the AI, A out. And again, these are equivalent. Whatever you do to this circuit, do exactly the same thing to the actual circuit, and whatever you come up with will be your parameter. So to start out with, let's take a fairly simple circuit. Again, this is a little bit silly, but it kind of illustrates the ideas. Find the two-port parameters for this circuit. So let's draw it down here. Here's a generalized two-port. Find the different terms. The first one, to find AI, I'll apply 1 volt at the output, measure this voltage. By voltage division, it's 3 over 2 plus 3, 3/5 of 1 volt, 0.6 volts. So AI is 0.6. That's one term. To find A out, what I do is apply 1 volt at the input, measure the voltage at the output. So if the input is 1 volt, by voltage division, it's 3/4 of a volt. So if this is 1 volt, I'll get A out. That's 0.75. To find Rn, this is where it's important that you short. Over here, I've got to short the output to get rid of this term. Measure the resistance at the input. So I short the output, measure the resistance at the input, and that's 1K plus 2K in parallel with 3K gives me 2.2K. So this is 2.2K. And the two have to match. To find the output resistance, you short the input, that gets rid of this term, and measure the resistance at the output. Do the exact same thing on your circuit. Short the input, measure the resistance here, and that's 2K plus 1K in parallel with 3K, 2750. So the two-port model will be this. There's your AI, A out, R in, R out. Now for this circuit, I'm not sure the two-port model is any simpler, But the later circuits, this will actually be useful. That just kind of illustrates how you find the different parameters. So here's another circuit. Find the two-port parameters. Again, this takes a while. I have to do 4 different circuit analysis problems, but it's just circuits. So in this case, to find AI, what I'll do is apply 1 volt at the output, find the voltage at the input. In this case, what I can do is at Vx, the currents have to add to 0. So the current left is Vx divided by 3K plus Vx over 3K plus this current. This current is minus 200 IB, and IB is this current, 0 minus Vx over 3K. Or what I could do is throw in a double negative. If I change the direction of IB this way, I've got to change this arrow. That throws in a double negative, same circuit. So this current is Vx over 3K plus 200. Vx over 3K equals 0. Solving, I get Vx equals 0. That's one way to solve. Second way to solve is to guess. If I can guess the answer, I don't have to solve. 0 is a pretty good guess. In this class, if you have no idea, guess 0. I'm going to guess 0 and see if it works. If Vx equals 0, then the current left is 0, current down is 0, current right is 200 times 0. 0 plus 0 plus 0 equals 0. 0 works. So Vx equals 0, Vn is 1/3 of Vx, also 0. AI equals 0. You can get that. That's actually something that's actually really good. To find the output gain, apply 1 volt at the input, find Vout. Here I'll do voltage nodes. The current left plus current down plus current right equals 0. Current left is Vx minus 1 over 2K. Current down is Vx over 3K. Current right is minus 200 times 1 minus Vx over 2K. Solving for Vx, I get 0.9951 volts. I can then solve for IB. That's 2.4 microamps. 200 IB is 1.9 is something times 4K gives you the voltage. So Vout is 1.97 volts. That must be Aout. This is an amplifier with a gain of 2. It's not really obvious, but it is. To find the input impedance, this is where there's a trick you can do. To find the input impedance, I short the output, find the resistance looking in, and I don't really know what to do with this circuit. In that case, what I can do is apply test voltage. Apply a 1 volt test and see how much current it draws. From before, if I do that, the voltage here is 0.9951 volts. The current is 1 volt over 1K plus 1 volt minus 0.995 volts over 2K. The current is 1.001 milliamp. That's this guy right here. The resistance then is V equals IR, 1 volt over 1 milliamp, 998 ohms. That's Rn. And that's a common trick. If you can't solve the resistance by inspection, apply a 1 volt test source and measure the current. That's actually how ohm meters work. They apply a test voltage, see how much current it draws, and then calculates the resistance. To find Rout, do the same thing. I short the input, find this resistance, and again, I don't really know what to do. That current source really confuses me. So if you don't know what to do, apply a 1 volt test. In this case, if this is 1 volt, Vx, I'm going to assume that's 0 volts, see if that works. If that's 0 volts, I have 0 plus 200 times 0 is 0. That works. So Vx is 0, this is 0, and all I see is 4 kiloohms. Where the current is 1 volt over 4K, 250 microamps. The resistance then is 1 volt over the current, 4 kiloohms. So the two-port model, this mess, which is kind of hard to analyze, is this mess, which is actually a whole lot easier to use. And this is getting ahead of ourselves a little bit. The reason for doing that is this is actually really easy to cascade. If I put two of these circuits back to back, build a multi-stage amplifier, this is actually not too bad to analyze. This has a gain of 1.97. The input impedance is 998 ohms. Output is 4K. Yeah, I misspelled 4K. 4K. Now find the Thevenin equivalent. Well, looking in is pretty easy, pretty obvious. Looking in, I just see 998 ohms. At the output impedance is pretty easy to see. For the output impedance, I set the input to 0. That makes this 0, this makes this 0, which makes this 0, which makes this 0. All I see is 4K. The gain then is if I apply 1 volt at the input, this becomes 1.97 volts. By voltage division, what is that, 998? Uh, 0.394 volts times 1.97 is 0.77 volts. So this is 0.77 Vn. That's the two-port model for two of these cascaded. And notice the two-port models were much, much easier to analyze than if I had these cascaded. That's where two-port models are really useful when you start cascading amplifiers. In Circuit Lab, I can do that as well. Suppose I have a circuit like this. Find the two-port model. Again, what I'm going to do is, here's the two-port model. This is also known as the small signal model. I've got my DC analysis and AC. The capacitors couple the AC to the DC, so this is really more of an AC analysis, or a small signal model. I've got my DC operating point, and I'm going to be perturbing it with a small sine wave, like a 1 millivolt peak-to-peak sine wave. Find the two-port parameters for this guy, going from Vin to Vout. To do that, I'll do 4 different tests. The first test, define AI, apply a 1 millivolt sine wave at 1 kilohertz at the input, measure the voltage at the output, make this an open circuit, or made it 10 mega ohms, basically open. And here's what the output looks like. It's a sine wave. The peak is 137 millivolts. So that's the gain. The input is 1 millivolt, output's 137 millivolts, A out is 137. And if you check, this is actually out of phase. When the input is plus, the output is minus. So the gain is actually minus 137. To find the output impedance, again on the two-port model, I've got this circuit. If I were to attach a 1K resistor to the output, the voltage will drop by voltage division. So let's try it. I add a 1K resistor to the output. The voltage goes from 135 millivolts down to 73. So that tells me by voltage division, without the 1K resistor, I've got 137 millivolts. With the 1K resistor, I have voltage division that produces 70 millivolts. Solve for R out. And doing some algebra, it'll be this, or the output resistance must be 930 ohms. Define AN. Apply 1 volt at the output, measure the voltage at the input, make this large, like 10 meg, and what I get is the input voltage is 9 nanovolts. So 1 millivolt produces 9 nanovolts. The gain is 0.009, basically 0. And the input impedance, again, since AI equals 0, here's my circuit, my two-port model. I want to find this term. One way to do that is add a 1K resistor in series. By voltage division, Vin will drop and Vout will drop. So if I apply 1K resistor at the input, this drops from 137 millivolts down to 71 millivolts. That lets you calculate Rn. So by voltage division, Rn over 1K plus Rn, normally the output would be 137 millivolts. The 1K drops the voltage down to 71 millivolts. Solving for Rn, I get 1119 ohms. So experimentally, I found the two-port parameters. And in the lab, you'd kind of do the same thing. Run 4 different experiments with your circuit. Again, I don't really care what this is, some black body. With those 4 tests, I can tell you what it looks like at the input, what it looks like at the output, and it'll be a two-port parameter, two-port model. So in summary, two ports are a generalized Thevenin equivalent. If you apply 1 volt at the output, I get the Thevenin equivalent at the input. If I apply 1 volt at the input, I get the Thevenin equivalent at the output. With 4 different tests, I can determine the 4 two-port parameters. So that's what a two-port is. It's kind of a generalized Thevenin that applies to amplifiers. We'll be using that in the following lectures to find the two-port parameters for common base, common emitter, and common collector amplifiers. And then using the two-port parameters, or two-port models, we'll look at what happens when you start cascading them. So that's lecture number 13 for ECE 321 Analog Electronics.